Okay, so we spent some time on our Zoom talking about impulse, and now I want to talk about work. And work goes really closely with impulse. They're very similar, okay? And the thing that you need to keep central in your mind is that when we're dealing with an impulse, okay, that's FDT, an impulse always changes momentum, okay? Now, if we don't integrate FDT and instead we integrate FDR, like so, okay, that's our work definition, and that changes kinetic energy, okay? So looking at force and time is going to alter a momentum value. Looking at force and distance is that ultimately going to alter a kinetic energy value, okay? So let's take a look here. All right, so we introduced these earlier, these relationships here when we introduced the sort of the first law of thermodynamics, our universal or our master energy equation. Okay, and we said that was going to be 1/2 mv final squared minus v initial squared. Okay, and then there's some change in gravitational potential energy, which you said was minus an mg delta H, and then we said minus some spring energy, which is 1/2 k x final squared minus x initial squared, and then if there's some losses due to friction, then we would have this term here, mu mg delta x, however far we go with the friction. Okay, so we introduced that, and I didn't tell you where those equation parts came from. Okay, we didn't tell you where does this come from, where does that come from, where does this come from. Well, here's where they come from. They come from thinking about the work done on a force. Okay, now when we're doing the work integral here, F and dr, direction matters. Okay, direction matters. With impulse, it's FDT. The force is a vector, but time is not. Time is a scalar. Okay, so when you do an impulse, you get a delta P. Whatever direction that is the same as your force. Okay, this is a little bit different because work is a scalar quantity. It doesn't have direction. Force has direction. My dr is my displacement. It has direction. Okay, so now let me speak to our Calc 3 people just for a quick second. Okay, what we're really talking about here is an F dot dr. Okay, that's our actual integral that we're dealing with. All right, in practice, what it means is, so if you haven't had Calc 3, that's okay. What it means is we need how much of F and D are in the same direction. Okay, so the parallel interaction of my force and my displacement is important. Okay, so let me get rid of some of this stuff here, and I'll walk you through how these integrals work. Things have gotten just a little bit messy on me here. Okay, how come I can't erase? Try this. Okay, there we go. Now we're erasing like a boss. Woo! Okay, I'm gonna get rid of that too, because my page is going to get messy. Okay, so that parallel, how parallel or not they are matters. Okay, so let's start with the work done by gravity. Okay, so our gravity, if we lift an object up in the air here, okay, we're going to have some displacement there, a delta y. If it's very, very tiny, if it's infinitesimally small displacement, then it's a dy. But what's the direction of gravity there? The direction of gravity is backwards. Okay, so as long as I lift it straight up, then what happens is the interaction of my force and my distance creates a negative sign. Okay. And that's where that negative sign comes from. All right. Now, then what we'll do is we're just going to end up integrating GD is a constant. Okay. And that just comes out front. All right. So we got our MG there. And then once we do this, dy just becomes a y. And we're going to have our limits between H initial and H final. Okay. And once we do that, then we get this expression right here. Okay. All right. And it works either way, whether you're going up or down. As long as you keep your final and your initial straight, then you're good to go. Okay. So if your final is higher than your initial, all right, then you've got a positive number in here. Okay. And that means you did positive work against gravity. Okay. Against gravity. So if the object had some, that's a positive number, but with the negative in here, ooh, let me go back on that, guys. That came out of my mouth in a goofy way. This term in here is positive, okay, but that term makes it negative. So if we're pushing against gravity, or not if we're pushing, but we take this box and we fling the box up in the air, okay, it's moving against gravity. And so there's some negative work that's done on it. And that means that my kinetic energy change is going to be negative. Okay. And it slows down. Okay, so that's what that means. On the other hand, if I start up here and it goes downwards, then what I end up is this term in here is a negative. Then with my negative here, it becomes positive, and my delta K is going to have a positive value. So I gained kinetic energy. Okay, so depending on which way I do my starting points, H initial, H final, then I'm either going to get positive work done by gravity, which is when it comes down, or negative work done by gravity, which is when it goes up. Okay. And this is a little bit of a tricky thing all the time with work. You got to imagine, where am I starting? Where am I ending? If you do positive work on the object, it speeds up. If you do negative work on the object, it slows down. Okay. All right. Let's look at a couple more of these, and I got to do some major erasing. I'm just going to try and keep this all on one page here. Okay, so the next one is with the friction. Okay, so I've got my box down here, and the box has a certain velocity, and then let's say it runs into an area where there's some friction. Now, once it hits that friction, then the force is back this way, but you can see my displacement is still this way. And so when I combine the force going one way and the displacement the other way, that becomes a negative again, which is how we've got this term in here. Okay, but you can see then we've got our force and our distance term there. And the same sort of thing, we're going to have some displacement here. That's going to be a positive number. That's going to turn it into an overall negative. So we're going to have some negative work there, which means it's going to slow down. Okay, so all that makes sense there. So that the friction is going to suck some kinetic energy right out of the thing that way. Okay, so that's how you think about that. There's no way to have turn that thing into a positive, because if my delta x was the other way, okay, if my delta x was actually this way, then that would mean my force is that way, and I'm back to where I started, where the work is a negative number. Okay, so time to erase. I need an erasing theme song. Maybe one of you can think about that. Okay, and then let's do the last one there. That's a spring. Okay, so I've got some object here, and maybe it's got some velocity. It's cruising along, and it's going to counter a spring, and it pushes that in. Okay, and so once again, you can see we're going to have our displacement is this way. However, our force is that way. Okay, so they're going to be opposite again. So that's why we get the negative sign in there. All right, but again, there's our spring. Here's our displacement. Okay, now in this particular integral, if you integrate x dx, you're going to get 1/2 x squared. Okay, let's just throw the k in there. Boom, boom. Throw our limits in there. X initial, x final, and presto, you get this guy right here. Okay. Now, the work done by a spring is similar to the work done by gravity. So it depends which way you're moving the thing, okay? Because we could have our spring compressed and have our box on that thing. And in that case, then it's going to push out with my force. And we could also have a delta x in that direction also. And so in that case, then the work will be positive on it, and we would that would pop out from this relationship here, whichever one of those was bigger. But a positive work, and that means we are going to increase our kinetic energy, so it speeds up coming off of that thing. Okay, so we got some take-home points here. All right, and that is the direction matters. Okay, so if you're moving against a force, you're going to slow down. If you're moving with a force, you're going to speed up. All right. Unless that force is friction, in which case it's only going to ever suck energy out of it. Okay. It's only ever going to reduce your kinetic energy. Okay. Now, let me erase one more time and let's go back and talk once again about gravity, because there is something kind of important you need to see with gravity. Okay, get rid of all my springs, my beautiful springs. All right, and that is this. What if our box actually has a velocity this way? And so it starts out, its center is here somewhere. Let's call that y initial, and it actually ends up over here, and over here we'll call that y final. Okay, does it matter that it went left or right? Okay. Well, check this out. What's my displacement going to be? My displacement is like this, okay? So let's call that delta R, okay? And that delta R is going to have a component this way, or delta R X, and it's going to have a component this way, isn't it? A delta R Y, okay? So what we could do is we could take our integral and we could set it up where the first integral that we do, we go minus mg dy. Okay, this is going to be for delta ry. And then the second integral we do is minus mg dy, and this one will go with our delta rx. Okay. Now, however, the Rx, that one, actually we would integrate in the X direction. Okay. Now, let's come back up and talk about this parallel business again. All right. If X is this way and gravity is this way, they're at right angles. So there's no amount of them that is parallel. All right. So this term right here is just going to be a big fat 0. All right. So in the end, all that matters is our direction relative to the force in question. Okay, just like that. All right, Calc 3 people. All right, so think about this. If we had an f dot dx, okay, like this, if those are perpendicular, what's the perpendicular result what's the dot product of two perpendicular vectors? It's 0. Okay, and so again, that thing is just going to go away. Okay, all right, now let me show you something here. We actually did something like this on the zoom, okay, except on the zoom, what we did was force versus time. All right, so I had the exact same looking shape. All right, an 800 Newton force is the max. Okay. And what we did with the impulse is we said over 1.5 seconds, it gets up to 800. then it stays there for a second and a half, and then it comes back down to 0. Okay. What we're doing this time is we're saying this force depends on the distance. Okay. So what might be an example of that? Well, great question. And I'm going to erase that because it's bugging me. All right. A railgun would be an example. Okay. So a railgun is a device where we've got 2 metal rails. All right. And these can be as long or short as you want them to be. And then you put an object in here between them. It has to be metal. And then you hook this thing up to a big voltage. Okay. And what'll happen is, you know, especially if you've got a magnetic field in there, is there's going to be a force that pushes this thing out. So as long as it's in contact with the 2 pieces of metal, all right, it's going to feel a force and it's going to accelerate out of there. Okay. Now, if you're bored sometime, Google railgun. All right. You'll see some awesome stuff. Okay. I don't recommend any of the DIY stuff. Look at the stuff being done by naval researchers and that sort of thing. But anyway, so in that case, we might imagine that for a certain distance across here, the force is increasing, and then maybe it's constant, but then right at the end, it's going to decrease. Okay, so our force is going up. Here it's going to be constant, and then our force is going to go down right at the end. Okay, so we might say then, so let's predict what that velocity is going to be. Okay, now the way we'll work this is very similar to what we did last time. Okay, because this integral is an area under a curve. Okay, so we can split this thing up into its bits. All right, turns out the area under this is 600. The area under here is 1200, and then 400. Okay, so that means my total area happens to be 2200. Whoops. I got too many 2's on there. 2200. Now, 2200 watts. Okay, well, I've got newtons this way, and I've got meters this way. So that's 2200 Newton meters, and a Newton meter is the same thing as a joule. Okay, so which is our unit of energy. Okay, but what do we do with that? Well, that value right there, that 2200, turns out to be our delta K. So that means we can take this thing, run it then as 1/2 m v final squared minus v initial. Oops, got a little sloppy there. Didn't like that. V initial squared, like so. Okay, like that. Then if we had the mass, we could plug in for that thing and we'd be good to go. Okay. Of course, we need initial speed too. Maybe we'll just throw some numbers in there just for fun. Let's suppose our mass is 10. That'll be easy to work with. All right. And our initial speed, let's start from rest. Okay. So now what I'm going to have is I'm going to have this delta K. All right. Times 2 over m is going to be v final squared. So that's 2 on to 2200 Newton meters, okay, which is a joule, over 10 kilograms. That's VF squared. All right. Anyway, when you do all that math, I worked it out earlier. What you get is 21 meters per second. Okay. Just like that. Okay, so now, I mean, one thing I wanted to add, you don't have to start at 0, okay? In our example with the railgun, it's going to start at 0, but that's not necessarily the case. I mean, we could, for example, we could maybe talk about a boat, and the boat's got some velocity, and then some wind picks up, all right, and the wind's going to apply a force, all right, like this, and then that's going to cause the boat to go even faster. Okay, so we could do that kind of thing too. So it's very versatile. All right, so one thing I want to take a look at here is the universal law of gravity. Okay, so let's suppose we've got an object here. All right, and I tell you what, I'll just call it M sub E. And we've got another object over here. We'll just call it M. Okay, and there's a distance between them. We'll call it R initial. And then what we're going to do is we're going to move this guy out to some other location. All right, and we'll call that R final. Okay, so there's some distance between those things, a delta R, like that. Now, what I'd like to do is I'd like to figure out what's the work done against gravity in that particular case. Okay, and so we set it up just like we've done before. Okay, we need a parallel interaction of our force here, and that'll be a little dr right there. We're going to go from some initial to some final. Okay, let's put everything in here the way we're supposed to. All right, the displacement is in the opposite direction of the force. Okay, so we're going to have minus g, mass of the Earth, mass of our other thing, over r squared dr. Okay. Now, I've got a bunch of constants. All right, boom, boom, boom. Those are all constants. They could come out. So what I'm basically left with then, if we pull out our constants, is this. dr. And again, we're going r initial to r final. Okay. Now, if you do the antiderivative of 1 over r squared, this term here, what you're going to get is 1 over r. Okay. Now, if that's a little rough for you, or whatever, just think of this inside my integral as 1 over r to the minus 2. Okay, dr. Okay, and so I got to raise that power to the r to the minus 1. Okay, and I end up losing my negative sign there once I do that. Okay, so the negative sign is going to cancel my sign out front. But what I'm going to get here is going to look like this. So I got G, mass of the Earth, M, and then I'm going to have 1 over R final minus 1 over R initial. Okay? Alrighty. Now, what I want to do then is I'm going to do a little bit of algebra here. And there's a reason for doing that, because we're going somewhere with this. If we were talking about a space, an orbital object, something going around the Earth, a satellite or whatever, and the satellite goes from one orbit to another orbit, then we could use this relationship, and we're good with that. But we're going to do something kind of different. All right, which is why I'm going to do this algebra next. All right, so let's retain our G, M, E, M. Okay, and I'm going to combine these things. So I'm going to have RF times RI. And then I've got RI minus RF, just like this. Okay. All right, now what we're going to do, let's say that I actually start on the surface of the Earth. So Ri becomes this right here. And let's say that our final is the distance of the Earth plus some other distance. Okay, we'll call it H. All right, just like that. And now let's plug that in and see what we get as a result. Okay, so I've got G, mass of the Earth, M. Put these things in here. Now, our initial is just R for the Earth. And we're going to subtract our final, which was R of the Earth plus some H. Okay, and on the bottom then, we're going to have R of the Earth plus H times R of the Earth. Okay, all we've done is we've plugged in into those things right there. Okay, now check this out on top. Okay, I've got RE here, okay, minus RE here, which is going to give me my H there. I mean, that's the only thing that's going to survive. Okay. So let's write that down. G, M-E-M. Okay, we're left with an H on top. It's a minus H, actually. Okay, and then I'm going to have RE squared plus RE times H. Okay. All right, now, whenever we use this expression mgh for dealing with gravitational potential energy or changes in height energy, h is tiny, okay? I mean, it might be 100 meters, but compared to the radius of the Earth, it is insignificant, okay? So that means that this term over here, we can throw that thing away. That gets thrown away, okay? Because it's so tiny compared to the radius of the Earth squared. That's going to be a really big number. All right. So now let's put that in and see what we get. Okay. So I've got G M E M minus H over R sub E squared. Okay. Now, if you go way back in your head or your notes, you'll see that we have seen this combination before. And that combination of numbers, if you run it through your calculator, you are going to get 9.81. That's little g. Okay, so what we've ended up with here is minus mgh. Okay, just like that. That's how you get from Newton's universal law to how we normally think about the force of gravity, mg, okay, and in relationship to energy. All right, so let's take a look. Anyway, you could follow this approach before I move on. You can do all kinds of things with this, okay, and what you need to remember is how to set it up, okay, how to set it up just like that, and then just follow it where the calculus and the algebra takes you, okay? Just be careful with your signs and that sort of thing. Okay, so let's pull back. Let's pull back and think about it this way. So what work does for us is it creates a way to assign a number to the changes we've been talking about, okay? And so anytime you got two objects interacting, if there's a force and there's motion involved, then we can calculate some work. And that means there's going to be changes in kinetic energy, changes in potential energy, that sort of thing there. Okay. So what we're going to do then now is we're going to take an object, this little square thing right here, and we're going to pull it, have some friction there, and just kind of think about what's happening with the work from all the different forces as we pull this thing, okay? All right, so here's our info right there. We've got the mass of the object. Our pulling force is 10. Okay, we're going to have some friction, and that's equal to 5. Now, that's not the coefficient of friction. That's just how much the friction is. All right, we don't know what the coefficient of friction is here, but we know that if we had it, we would get 5. Okay, so if we wanted to work hard, we could go backwards through this thing and figure out what it's going to be. Okay, we're going to have some weight, okay, mg, and here, and then the normal force here. Okay, so if we're pulling this thing all the way over here, okay, that's our distance. Okay, what we want to do is calculate the work done by each one of these forces. Okay, so I start with my pulling force. Okay, it's pulling 10, a distance of 3. Okay, that was up here. Then that gives me 30 joules right there. All right, now the work done by gravity, okay, it's the weight, there's M, here's G, but it doesn't go up or down, does it? okay? Because all that matters is how much it moves relative to that force, okay? So in that case, it's 0. They're perpendicular. So I don't get any energy. That doesn't affect my kinetic energy at all. If we look at the normal force, okay, the normal force would be the same thing here, this. And once again, there's no motion relative to the direction of the normal force. So we get 0 here. All right. Finally, let's see what's happening with our work done by friction. Okay. So now the force is backwards, but the displacement is forwards. So we've got to have a negative sign in there. And so we're going to have negative work, just like that. Okay. So if we add all this up and we think about what we call net work, okay, which is going to be the total amount of work done by all my different forces, okay, we're going to have 30 plus 0 plus 0 minus 15 gives us 15 joules. Okay, and then we could use that to calculate the change in kinetic energy. All right, and this tells us we have a positive change, so that means the thing is going to speed up. Okay, now we could have figured that out pretty easily already because we know the pull, capital F pull, is 10 and the friction is only 5. So our net force here in the x direction is actually 5. So we anticipate that it should accelerate. Okay. Okay, so let's look at another one here. Okay, now my pulling force is up at an angle. Okay, it's going to be 6. So that means up here we're pulling with 6. Okay, now our displacement is still here to the right. Okay, now since we're pulling up somewhat, our normal force is going to be a little bit less. Okay, and that means our friction force is going to be a little bit less. Okay, all those sorts of things. Now again, I'm just made up a number here. Let's say 3. Okay, for our frictional force back there like this. Okay. So the work done by the pulling force, what we need is the amount of the pulling force that's in the same direction as my displacement. Okay, my displacement is 3. My pulling force is 6, but I've got to throw in the cosine there, because that's going to get me this horizontal component of my pull. Okay, so I have to use that horizontal component of my pull in order to calculate the work that we do, and that's a 9. Okay. Once again, the weight, there's no motion that way. The normal force, even though the normal force is more complicated, there's still no motion that way. And so we still don't get any contribution. Now, jumping to the friction, then, we still got the situation where our force is one way, our motion is the other. Okay, so we end up with a negative amount here. So, what is our net work in this case? Well, it's 9 plus 0 plus 0 minus 9 is 0. Okay, so this thing is not going to be speeding up or slowing down, either one. Okay, now it would not be a surprise to figure out that when we look at this x component of our pulling force, guess what? That turns out to be 3. Yeah, that turns out to be 3. Okay, and so if we're pulling 3 one way and 3 the other way, then it's in equilibrium. Okay, so it isn't going to speed up or slow down. Okay, so that works out just fine. All right, let's look at one more case. We're almost done here. Okay, so we're pulling with 6, just like we did before, but now for some reason we have a lot more friction involved. So our frictional force is pretty big somehow. Okay, now let's see what happened. Okay, the pulling force at the same angle gets us to the 9, same answer we had before. Once again, the weight and the motion are perpendicular. The weight and the normal force are perpendicular, or the normal force and the displacement our perpendicular. Okay, but take a look at our friction. We've got 7 newtons backwards, a displacement of 3 forward, so we get negative 21 is our force from our friction. So okay, you can see what's happening now. The net force. Now we're looking at 9 plus 0 plus 0 minus 21. Okay, and so if I do my math right there, then that means negative 12 joules is our delta K. So this thing's going to slow down. Okay, and again, looking at it from the perspective of force makes sense because this pulling component up here, all right, is only 3 like we had last time. Okay, so 3 one way, 7 back the other way. That's not going to do anything but slow us down. Okay, there we go. All right, so that is the story there. Let me just one more time. Let me come back. Come back. Whoop. Nope, that's what I wanted. Okay. All right, so this is your most important idea right here. Impulse and work. They're very similar. Very similar. All right. Keep it straight in your head. Okay, P goes with momentum. See what I did there? All right.